Hello students, I Dilip Kumar Jain PGT Physics, Kendriya Vidyalaya number 1 Pratapnagar, Udaipur. I am here with you student with chapter number 5 Magnetism and Matter part 1. इसके जो इम्पोर्टेंट टॉपिक्स जो हम इस सेशन के अंदर कवर करेंगे वो हैं मैग्नेटिज्म. Second one, the properties of magnetic field lines. Third one, bar magnet as an equivalent solenoid. Fourth one, current loop as a magnetic dipole and its magnetic dipole moment. Fifth one, torque on a magnetic dipole, that is bar magnet in a uniform magnetic field. Magnetic potential energy. Next, magnetic field intensity due to a magnetic dipole, that is bar magnet, along its axis and perpendicular to its axis. Magnetism and Gauss law. And last topic is the electrostatics analog with the magnetostatics. First one, we start with the magnetism. The earth behaves as a magnet with the magnetic field pointing approximately from the geographic south to the north. जैसा कि हम जानते हैं अर्थ जो है मैग्नेट की तरफ बिहेव करता है और उसका जो मैग्नेटिक फील्ड है उसका डायरेक्शन जो है ज्योग्राफिक साउथ से नॉर्थ डायरेक्शन की तरफ होता है. सेकंड पॉइंट, व्हेन ए बार मैग्नेट इज फ्रीली सस्पेंडेड इट पॉइंट्स इन द north south direction. The tip which point to the geographic north is called the north pole and the tip which point to the geographic south is called the south pole of the magnet. Third point, there is a repulsive force when north pole or south pole of two magnets are brought closer together. Conversely, there is an attractive force between the north pole of one magnet and the south pole of the other magnet. Means there is a repulsive force between like poles as north pole or south pole, and there is a attractive force between two magnetic poles when magnetic poles are unlike. One is north pole, second is south pole, or first is south pole and second is north pole. Next, point number 4, we cannot isolate the north and south pole of a magnet. If a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic north and south poles known as magnetic monopole do not exist. Very important, bar magnet is a elementary unit in electric dipole. We cannot separate north pole and south pole. When we compare it with the electric dipole is not a fundamental unit of electrostatics. It is made of two different things, different charges, positive charge and negative charge. But in magnetism, monopoles do not exist. मीन्स नॉर्थ पोल और साउथ पोल जो हैं अलग अलग नहीं हो सकते. अगर एक बार मैग्नेट है उसको अगर बीच में से काट भी दिया जाए तो अपन को दूसरा दो बार मैग्नेट मिलेंगे, उसकी स्ट्रेंथ जो है पहले वाले से कम होगी. फिफ्थ वन, इट इज पॉसिबल टू मेक मैग्नेट आउट ऑफ आयरन एंड इट्स एलो the bar magnet. The pattern of the iron filling suggests that magnet has two poles similar to positive and negative charge of an electric dipole. Iron filling surrounding a bar magnet जो है एक्टिविटी अपने क्लास 10th में की थी, उसमें जो आयरन फिलिंग्स जो अरेंज होती है उसको अगर अपन अच्छे से अगर देखें तो अपन देखेंगे कि जो मैग्नेटिक फील्ड लाइंस का जो कंसंट्रेशन है वो टू प्लेस पे ज़्यादा होगा. One pole is destination at north pole and other is south pole. When suspended freely, these poles approximate towards the geographic north and south pole respectively. The magnetic field lines. Here three important magnetic field lines. First one is due to a bar magnet, second one is a current carrying finite solenoid, and third one is electric dipole. On observing figure A and B, we find that the magnetic field lines pattern is identical, but in third case the magnetic electric field line in first two A and B is what electric field lines, but in third one is what magnetic field line. What is the basic difference between magnetic field lines and electric field lines? Electric field lines can be called as a force line, but the magnetic field lines can never be called as a force line. In chapter number 4, we already studied that the magnetic force is never in the direction of magnetic field lines, but electric force is always in the direction or opposite of the electric field lines. Properties of magnetic field lines. First property, the magnetic field lines of magnet or a solenoid form continuous closed curve. This is unlike the electric dipole where these field lines begin from a positive charge and end on the negative charge or escape to infinity. मैग्नेटिक फील्ड लाइंस की फर्स्ट प्रॉपर्टी है कि जो भी फील्ड लाइंस होंगी वो हमेशा क्लोज लूप बनाएंगे, लेकिन इलेक्ट्रिक फील्ड लाइंस के अंदर ऐसा नहीं होगा. अगर क्लोज लूप बनाएगा तो वो जो है इलेक्ट्रिक फील्ड लाइंस नहीं होगी. सेकंड पॉइंट, द टेंजेंट टू द फील्ड लाइन एट ए गिवन पॉइंट रिप्रेजेंट द डायरेक्शन ऑफ नेट मैग्नेटिक फील्ड बी एट दैट पॉइंट. ऐसा ही जो है आपका इलेक्ट्रिक फील्ड के अंदर भी था. थर्ड पॉइंट, द लार्जर द नंबर ऑफ फील्ड लाइंस क्रॉसिंग पर यूनिट एरिया, द स्ट्रॉन्गर is the magnitude of magnetic field B. In figure A and B, B is larger around region 2 than in region 1. So in last diagram we can see here 1 and 2. 1 and 2 in A figure and B figure we can see that the magnetic field line is 1 is more and at 2 is less, means B is larger around the region 2 than in region 1. Fourth one, the magnetic field lines do not intersect. If they did, the direction of magnetic field would not be unique at the point of the intersection. If they do intersect at a point, compass will show two direction, and which is impossible. Now, bar magnet is an equivalent solenoid. We study in last chapter, chapter number 4, that Ampere's hypothesis that all magnetic phenomena can be explained in terms of circulating currents. Recall that the magnetic dipole moment M associated with a current loop was defined to be M equal to NIA, where capital N is the number of turns in the loop, I is the current, and A, capital A, is the area vector. The SI unit of magnetic moment is ampere into meter square. As we seen that the resemblance of magnetic field lines for a bar magnet and a solenoid suggests that a bar magnet may be thought of as a large number of circulating current in analogy with a solenoid. Now we derive a relations. In the diagram, one solenoid is given of length 2L and at its radius is what? A. So consider a solenoid of length 2L, radius is A, and having n turns per unit length. Small n. Small n means what? Number of turns per unit length. It is carrying current I. जो इस डायग्राम के अंदर है अपने पास क्या है? एक सोलिनॉइड है, उसकी लेंथ कितनी है? 2L है, रेडियस क्या है? A है, और नंबर ऑफ टर्न्स क्या है? स्मॉल n, और इसके अंदर करंट जो फ्लो हो रहा है वो क्या है? I. We have to evaluate the electric field at point P at a distance r from the center of the solenoid. जो सेंटर ऑफ सोलिनॉइड है O से r डिस्टेंस पर एक पॉइंट P है. इस पॉइंट P पे अपन को इस सोलिनॉइड के कारण मैग्नेटिक फील्ड को कैलकुलेट करना है. इसके लिए अपन क्या करते हैं देखते हैं. कंसीडर ए सर्कुलर एलिमेंट ऑफ थिकनेस dx ऑफ द सोलिनॉइड एट ए डिस्टेंस x फ्रॉम इट्स सेंटर. सोलिनॉइड के सेंटर O से x डिस्टेंस पर एक स्मॉल एलिमेंट जिसकी थिकनेस dx है उसको अपन लेते हैं. इस स्मॉल सर्कुलर एलिमेंट के कारण द magnitude of the magnetic field due to this circular loop carrying a current I is given as dB equal to mu 0 dx n I a square upon 2 r minus x whole square plus a square whole power 3 by 2. This is the expression coming from the magnetic field on the axis of a circular current carrying loop. The magnitude of the total field is obtained by integrating over all the elements from x equal to minus L to x equal to plus L. As we see from the diagram, this solenoid is symmetric about the O point. So B equal to mu 0 n I a square by 2 integration from minus L to plus L dx upon 2 r minus x square plus a square whole power 3 by 2. Next, the magnitude of the total field is obtained by integrating over all the elements from x equal to minus L to x equal to plus L. B equal to mu 0 n I a square by 2 integration from minus L to plus L dx upon 2 r minus x square plus a square whole power 3 by 2. Consider far axial field of the solenoid. Now we assume that the point of observation where we want to find the magnetic field is much larger than radius of the solenoid as well as total length of the solenoid. Hence we have r minus x whole square plus a square whole power 3 by 2. A square is 0, x square 0, so one simply we get r cube. So we get B equal to mu 0 n I a square upon 2 r cube minus L to plus L dx. Now on integration dx we get x, and on putting this upper limit and lower limit we get L minus L. So we get B equal to mu 0 n I a square upon 2 r cube into 2L. Now the magnitude of the magnetic moment of the solenoid is m equal to total number of turns into current into cross-sectional area. M equal to what? NIA. So here n into 2L. N into 2L is what? Capital N. Total number of turns into I into pi a square. So to get the pi a square, what we do? We multiply above expression its denominator and numerator by pi. Therefore, we get the magnetic field as now mu 0 upon 4 pi 2m upon r cube. How come this 4 pi? Just multiply 2 by 2. So B equal to mu 0 upon 4 pi 2m upon r cube. This is the expression for magnetic field due to a solenoid on the axial line at a distance r from the center. This magnetic field is also the field due to a bar magnet of magnetic field M. Next topic is torque on a magnetic dipole bar magnet in a uniform magnetic field. This expression is similar to torque on a electric dipole in a uniform electric field. In this condition, we can see that a magnetic field B is there, and we put a compass dial in which the north pole, the magnetic axis making an angle theta with the B. In this condition, this compass dial will experience a torque. The torque on this dial is given by tau equal to m into B. Its magnitude is tau equal to mb sin theta. Here tau is restoring torque and theta is the angle between m and B. So therefore in equilibrium what we get? I d square theta upon dt square equal to minus mb sine theta. From the definition, tau equal to I alpha. Equal to what? I alpha. This I is what? Moment of inertia. D square theta upon dt square is what? Alpha. We know that d theta upon dt equal to what? Omega, and d omega upon dt equal to what? Alpha, angular acceleration. So therefore, in equilibrium, I d square theta upon dt square equal to minus mb sine theta. Negative sign with mb sine theta implies that the restoring torque is in opposition to deflecting torque. For small value of theta in radians, we approximate sine theta equal to theta. So we get I d square theta upon dt square equal to minus mb theta, or d square theta upon dt square equal to minus mb upon I theta. This represents a simple harmonic motion. Simple harmonic motion. The square of the angular frequency is omega square equal to mb upon I, and so this expression d square theta upon dt square equal to minus mb I theta. This expression we study in 11th class. जब अपन सिंपल पेंडुलम पढ़ते थे उसी समय ये एक्सप्रेशन आता था, तो जो कि यह सिंपल हार्मोनिक मोशन को बताता है. अगर उससे कंपेयर करें डी स्क्वायर थीटा अपॉन डी टी स्क्वायर इक्वल टू माइनस ओमेगा स्क्वायर थीटा, देन ओमेगा स्क्वायर इक्वल टू व्हाट? एम बी अपॉन आई. एम इज व्हाट? मैग्नेटिक moment, b is magnetic field, and I is what? Moment of inertia. So tau equal to 2 pi upon omega. We substitute the value of omega equal to under root mb upon I. So we get expression t equal to 2 pi under root I upon mb, or by squaring we get the expression b equal to 4 pi square I upon mt square. This formula is very important when we solve the example. First example is based on this formula, b equal to 4 pi square I upon mt square. Once again, what is I? I is moment of inertia. M is what? Magnetic moment. T is what? Time period. V is what? Magnetic field. So P equal to 4 pi square I upon mt square. Next, magnetic potential energy, similar to electric potential energy. We studied in chapter number 2. Calculation method of calculation is same. The magnetic potential energy um is given by equal to tau theta d theta. We substitute the value d theta equal to mb sin theta. On integration we get minus mb cos theta, or this can be written as a scalar product of minus m vector dot b vector. Now, when the needle is perpendicular to the field, expression of the potential energy show that potential energy is minimum, that m equal to mb minus mb at theta equal to 0, most stable position, and maximum equal to field. Okay, now so we are getting what is the most stable position and most unstable position. बहुत सी बार एग्जाम के अंदर पूछा जाता है what is the angle theta when bar magnet is in stable position or unstable position, or stable equilibrium or unstable equilibrium. अगर stable equilibrium है तो वैल्यू याद रखना थीटा इक्वल टू कितना 0 डिग्री, और अनस्टेबल इक्विलिब्रियम या अनस्टेबल इक्विलिब्रियम है तो थीटा इक्वल टू 180 डिग्री. Next one, magnetic field intensity due to a magnetic dipole, bar magnet, along its axis and perpendicular to its axis. The magnetic field at large distance due to a bar magnet of magnetic moment m can be obtained from the equation for electric field due to an electric dipole of dipole moment p by making the following replacement. इलेक्ट्रिक डाइपोल के अंदर अपन ने इलेक्ट्रिक फील्ड का एक्सप्रेशन अपन ने डिराइव किया था ऑन एक्सिस और ऑन इक्वेटोरियल। उस एक्सप्रेशन के अंदर ई को रिप्लेस करना है बी से, पी डाइपोल मोमेंट, इलेक्ट्रिक डाइपोल मोमेंट को रिप्लेस करना है मैग्नेटिक डाइपोल मोमेंट, और 1/4πε0 को रिप्लेस करना है μ0/4π। देखते हैं क्या होता है। We can write down the equatorial field BE of a bar magnet at a distance r, for r is much greater than L, where L is the time is the size of the magnet or length of the magnet. Before writing the expression BE, first we recalling what are the results in case of electric dipole. First one, at a point on the dipole axis, E equal to 2p/4π epsilon naught r cube. R is much greater than A, where A is what? Just a distance of any charge from the center of electric dipole. So here what we do, in place of E we write BE, and second expression, at a point on the equatorial plane, E equal to -p/4πε0 r cube. In place of E we write BE equal to minus, in place of P we replace M, and 1/4πε0 we write μ0/4π r cube. So this is the expression for equatorial field BE due to a bar magnet. Likewise the axial point field BA, एक्सिस पॉइंट के ऊपर मैग्नेटिक फील्ड बार मैग्नेट के कारण क्या होगा, उसका एक्सप्रेशन में भी अगर इसी प्रकार का रिप्लेसमेंट किया जाए, फर्स्ट वन, एट ए पॉइंट ऑन द डाइपोल एक्सिस E इक्वल टू 2p/4πε0 r क्यूब, तो BA इक्वल टू व्हाट, μ0/4π 2m/r क्यूब। सिंपल सा यहाँ पे रिप्लेसमेंट करना है, क्या करना है देखिए, E रिप्लेस बाई बी, पी रिप्लेस बाई एम, 1/4πε0 रिप्लेस बाई μ0/4π. In this condition we just substitute the value and we get the magnetic field on the axis and equatorial point due to a bar magnet. Next, magnetism and Gauss law. Consider a small vector area element delta S as shown in the figure, closed surfaces in figure 5.6. The magnetic flux through AS is defined as delta phi equal to B dot delta S, where B is the field at delta S. We divide S into many small area elements and calculate the individual flux through each. Then net flux phi B is given as summation of all delta phi B's or summation all B dot delta S equal to 0. Compare this with the Gauss law of electrostatics. The flux through a closed surface in that case is given as summation E dot delta S equal to Q/epsilon naught. Thus, Gauss law for magnetism, the net magnetic flux through any closed surface is 0, because B dot delta S equal to 0, delta S cannot be 0, so B equal to what, 0. So Gauss law for magnetism is the net magnetic flux through any closed surface is 0. What is the Gauss law for electrostatics? The net electric flux through any closed surface is 1/epsilon0 times of total charge enclosed by the Gaussian surface. One more thing, if some electric bar magnet or magnetic dipole is present in this one, in this condition, if we consider north pole as a positive magnetic strength and north pole as a negative, then total effect is what, 0. So no magnetic flux through any closed surface. So Gauss law for magnetism is the net magnetic flux through any closed surface is 0. Next, the electrostatic analog with the magnetostatic. Now we compare electrostatics and magnetostatics. First one, electrostatics and magnetism. 1 upon epsilon 0 is equivalent to mu 0. Epsilon 0 is permittivity of the free space, mu 0 is permeability of the free space. Dipole moment P, and here in magnetism is what? Magnetic moment. P is defined as Q into 2A. M is defined as what? NIA. Equatorial field for a short dipole in electric field and magnetic field. We already discussed axis field for a short dipole. Already we discussed in last section. And external field के अंदर अगर इलेक्ट्रिक डाइपोल और मैग्नेटिक डाइपोल को रखेंगे तो इट विल एक्सपीरियंस टॉर्स वी डिराइव ऑलरेडी टॉ इक्वल टू पी क्रॉस ई एंड इन केस ऑफ मैग्नेटिज्म एम क्रॉस बी एक्सटर्नल फील्ड that is potential energy, electric potential energy is what? Minus P E or minus P E cos theta. In case of magnetism it is minus M B, M dot B or M minus M B cos theta. Thank you.